topology of the network. They're trying to create an instance of index coding, all right, and that have similar properties, right? And the question is, kind of the view of yesterday's panel, why we really need it, right? So it's kind of completely useless, right? So looks like, right? So why we would create another instance of index coding, right? But it's really useful to establish connection between those two problems. And for example, one of the properties of network coding will be kind of by using this reduction, we can prove certain properties of index coding by just copying or kind of reducing from, or kind of by leveraging the properties that are already known for network coding. For example, for network coding, there was a long series of work that shows the advantage of nonlinear coding over linear coding. So we can basically establish the same property for index coding, right? So basically, whenever we'll hold, like, of course, we need to be careful, kind of, and consider the limitation of this reduction, but in general, we can kind of show that the same property that already established, right? So people work hard to establish those properties. They can be basically the same property hold. It's the same properties hold for the index coding as well, right? So this is basically idea. And another advantage is that vector linear coding is better than scalar linear, and this can be established in different ways, but one of them by just reducing from the network coding. Okay, and the follow-up work, kind of not very recent, not very kind of old, like just 1 year ago, they showed equivalence for general nonlinear decoding functions. But the reduction itself is pretty similar, and just proof more complicated because you need to consider any nonlinear function, which kind of very wide class of functions. Okay, so in the next few minutes I will also show a reduction, but from different objects, from different mathematical objects, and they called matroids. And that's also very interesting because matroid theory being around for 100 years, right, or maybe less, but also a lot of results known for matroids. And we can, if we establish some relations between problem of linear representation of matroids and to the index coding problem, we can actually leverage those results, right? So we can say that basically they represent the same problem. So many of the properties of matroids will be for linear for index coding as well. So just kind of reminder for matroids, probably many of you are not familiar. So it basically generalizes notion of linear independence. So if you're looking, for example, on a linear space, right? So we have a vector, some vectors in a linear space, and in this case it's just two-dimensional linear space, just an R2. So we can basically list as a set of independent vectors, right? So kind of each vector by itself will be independent, and some pairs of vectors will be independent. Of course, it's kind of linear space of dimension 2, so no three vectors will be independent, but pairwise it will be independent, the vectors are independent. And basically, those linear independent sets satisfy the following condition that if A is independent, and then we have some subset of A, that this subset will be independent as well. And then if we have two independent sets, one is like lower dimension than the other, or low cardinality than the other, then there is some elements that belong to B that I can add to A, such that A plus this element will be independent. So it's pretty obvious for just traditional linear space, right? But it can be generalized. So matroids is exactly the same thing, but it doesn't require any linear relation between those, right? So it's basically it's a couple between we have some finite set which is called ground set, and then just list the connection of ground set, linear independent, independent sets, right? So not necessarily linear, right? So just connection of independent sets that satisfies those following basic axioms, right? So one of them is that empty set must be independent, and then exactly the same as you said, right? So if you have an independent set, then any subset of the set will be independent, and then given two sets, one smaller than the other, we can just grab one of the elements from larger set, add this to the smaller set, it will still be independent, right? So it's basically, you see that it holds for this linear independence, but it's more general, so not necessarily every matroid will be representable using linear space, right? And it's one of possible definition of a matroid, right? So it's kind of can be defined in different ways, but it's one of the definition we can use. Okay, so the problem that people work on it for a long time is basically if matroid is representable linear space. It's a natural question to ask, right? So once we have this generalization, so you define matroid by some collection of those spaces, and I kind of can I find some linear space that basically this matroid will capture those independent sets of this linear space, right? And it's well known that some of the matroids are representable over some spaces, over finite fields, and some characteristics. For example, this matroid, which is called non-finite matroid, but the way it's kind of graphical representation of this matroid is basically saying that if those three elements of the same line, they must be dependent. If it's not belong to, so any three elements that don't belong to the same line, they must be independent, right? So for example, element 1, 6, and 7 are independent, right? And this is just kind of, instead of enumerating those independent sets, I can just use this graphical representation. But also here you see that each vertex is annotated by some vectors, and it basically shows this representation of this matroid in a linear space, right? This dimension 3 over GF3. Right, and we have bases x1, x2, and x3, and you see that every three vertices on the same line, they will be dependent over GF3, right, and every three vertices that don't belong to the same line will be linearly independent over GF3. So it's basically well known that some of the matroids are represented over field with odd characteristics, some of the matroids you can see represented field with even characteristics. Is fascinating theory, right, and basically kind of what we want to do here is basically use those matroids to build instances of index coding problem, and then we can say about this vertex index coding problem that this problem cannot be really solved. Okay, it doesn't have a linear solution of a field of certain characteristics. Right? This is basically the goal. Okay, and this is just a formal definition, but you already have an intuitive understanding what is it. Okay, so how we build a reduction, again, it's the same thing, right? And I will go really quickly because it basically uses pretty much the same ideas we used for reduction from a network to the instance of index coding problem. So we're starting with a matroid and we're trying to build an instance of index coding problem such that a linear solution exists for this index coding problem if and only if there exists a linear representation of this matroid over the same field. Right? So this is the idea. And again, like we built in this instance, so we need to define the set of packets. So we'll have obviously packets for each element of this matroid. So in this case, we have seven elements in the ground set. So we have 7 packets, kind of red packets, Y packets. Thank you. And then we have a set of bases, right? So we have a packet that correspond to the basis of this linear space that we're trying to use. Right? In this case, it will be 3 vectors because it's a vector of dimension 3. So those will be set of messages, right? The set of messages, we didn't say anything yet about clients, but the set of clients will be chosen such that force certain restrictions on the solution of index coding problems, so it will be also useful for representing matroid. Okay, is it following me? Okay, so and again, reduction is pretty similar to what we did yesterday. So one, we have this client that demands client Y and have side information of all packets and X. And this is the forces that, if you look again on this matrix, so every encoding matrix will have this form. Part of this will correspond to messages in Y, and another part will correspond to messages in X. And since we have a client that requires all messages in X and needs messages in Y, this part of this matrix must be invertible, right? So if I just erase those columns, because this client knows all packets in X, so it can basically exclude all those variables, right? This client will be able to diagonalize this matrix, so I can represent the solution. So it basically forces the solution of index coding problem to be representable over this form, right? I can represent it over this basis, and then I can use another client to force the dependency constraints on this matrix, right? Okay, so the solutions will be in this form, and then I can represent by diagonalizing this, right? It will be, each row will correspond to yi plus a certain function. And now I can force some dependency relations on those functions, so I can guess that this function will correspond to linear representation of this element of the matroid, right? So for example, for y1, this function will be corresponding to linear representation of not 1 in the matroid. Okay, and so now I need to force the conditions. First of all, I need to consider dependent sets, and I need to consider independent sets. So let's start with independent sets. So how I can force a condition that functions that corresponding to independent sets are independent by adding this client that requires x, but has those. So for example, okay, so in this example we have a set that includes element 1, 2, and 3, and this element is independent by the definition of the matroid. So now I need to force that the functions that correspond to elements of this set are independent, right? And then we require this basically in this. Introduce a new client. This client has y1, y2, and y3. So this client will be looking only on this part of this matrix because it's no x1, y1, y2, and y3. It doesn't know all of those elements, so all those elements will be useless for this client. All those rows will be useless for this client. And this client knows y1, y2, and y3, so this client will only have access to basically this submatrix. And the requirement is that this matrix must be invertible because this client needs all of element of x. So I'm sorry, it kind of looks like rectangular, but it will be square matrix, right? It will be 3 by 3. So we have 3 by 3 matrix, right? And this must be invertible. And this will basically require these functions that correspond to those, which correspond to rows of this matrix. They must be independent, right? So this is how I force a condition on independent sets. So for dependent sets, I want to force a dependency condition. And this is similar as we did last time, yesterday, right? So I'm adding client that knows y1 but needs, requires y1 but needs y2 and y3. Again, this client, all those rows will be relevant, right? But now we need dependency because it doesn't know one of the y's, so it doesn't know y1, right? So it's basically, this is unknown, and actually it's what it wants to get. Okay, and it's only, you can get it because he can substitute this and can substitute this, but it's only will be able to decode this if this row is a linear combination of those two, right? So it has this alignment in this row. Okay, and this is basically just an example if you want to look later on in the slides. I don't want to go over it. And the applications, we can all kind of open the books on matroids and like pick your favorite matroids, for example, non-purpose matroid. And for example, for this non-purpose matroids, it's known that there is no representation, kind of scalar representation, right? So you can only be representable if we have two vectors corresponding to each element of this matroid. So in our terminology is a vector linear of k is equal to 2, right? And so it only has the scale 2 linear representation over JF3, and this basically implies that index coding behaves the same way, right? So I can build instances of network coding, index coding that only be solvable through vector linear coding, but not scalar linear coding. Okay, so that's probably like what I wanted to say about matroids and reductions, right? We'll have a little bit more reductions, but if you kind of lost me, this is time to reconnect and ask questions. And I'm just going to the new topic. No questions? Was clear or it's just lost? What's the morning? Okay, so let's then go to another problem, and it will be cooperative data exchange programs that I'll talk about this a little bit, kind of probably most of the time until the end of this lecture. And this problem is kind of similar in nature for index coding, and that we have a set of clients that want to exchange some information, but now we take access point out of the picture, right? So the clients just want to exchange information between themselves, right? So we don't have some super clients that broadcast and everybody just get to listen. Now everybody can broadcast, but we don't have the super clients that knows everything. This is basically what is the difference in this problem. So in this problem, we basically have a subset of clients, and each client, so it's a set of clients, and each client has some subset initially from the ground set, right? So this is basically what was a has set in the index coding problem, but now it will be just one set, because each client will want to decode all the packets, right? So in some sense, this problem is easier than index coding, because in index coding, every client wanted to some particular packet, right? So in this problem, everybody wants everything, right? And this makes this problem actually easier, right? So if you know, like in a network coding, right? If you have a multicast case, so everybody wants to do everything, this problem is solvable and well understood, right? But if you have kind of multiple unicasts, so different people want different things, right? In this case, this problem becomes extremely hard, right? It's very little to know about it, right? So in this case, like index coding problem, you can think about it as equivalent of a general network coding problem with multiple unicasts. And cooperative data exchange is kind of like a multicast case, right? But it's different from a traditional single source multicast. It's kind of like a multi-source multicast, right? Because we don't have all information available in all nodes. So I don't have like really luxury sometimes to just assume that I can create any code I like, because I have constraints, right? So data will come from different sources, and basically I kind of need to design a scheme that will satisfy this constraint. I have some problem with it. It's kind of a little bit annoying. Thanks. Yeah, so just kind of it turned off. It's okay, okay. So again, like just to understand this problem, so we have multiple clients. Each client knows a subset of the set and want to receive rest of the buckets, right? Because here we have this client knows x1, x2, and x3, so it needs to obtain x4 and x5, right? So it's basically just writing one set because we just need to receive the content, right? So now those clients can exchange this data over a shared broadcast channel. Right, the broadcast. So, for example, if this client transmits, this data will be received by multiple clients, by everybody else, right? Okay, and they need to take turns, okay, because they share this channel. For example, this is a solution to this problem. This client will transmit this x1 plus x2 and x3. This will make this transmission. This will make this transmission, and you can verify that everybody will be able to decode everything. So, for example, if you're looking on client 1, it will use those two transmissions made by client 2 and client 3. And basically we'll be able to decode x4 and x5 because it knows x1, x2, and x3. Okay, and it can decode x4 from here because it can substitute x2 and x3. It can decode x5 from here because it can substitute x3. And x4 is just decoded, right? So basically you can verify its whole spread. Okay, and only one function of this broadcast is in a time slot, right? So kind of how we can motivate it. So we can motivate it like for practical scenarios, right? So like you always need to switch to dimmer. Okay, so one of the motivations. Okay, just 1 minute. Okay, yeah. Okay, so how we can motivate this program? Okay. Suppose we have again the scenario that all of you have cell phones and we have tower and all of us want to watch some movie, right? So kind of in today's cellular network, unfortunately it's done not very efficiently, like each of you will try to download it separately. You can think about more efficient scheme and was proposed I think like LTE. It's kind of like broadcast, right? So everybody like the station broadcasts those movies to you, right? Probably some of you will miss some of the packets, right? So now what we can do, so suppose like it was 3 packets in total, but everybody lost like different packet because the channel condition will depend on the receiver, right? So it's each receiver might not be able to decode some of the packets. And then of course we can go and again and ask the base station to retransmit some code combination, and so kind of more similar to index coding problem. Or we can say, okay, let's try to reconcile. Let's forget the base station. Okay, let's try kind of share those between us, and basically try to decode this movie locally, right? In this case, it's exactly like similar to this problem, and again, it's kind of really abstraction of this problem. Yeah, so it's kind of in practice, right? It's always have some. I can actually use normal example. Right. Okay, and so is it clear like the motivation of this problem, right? So it's and it's actually there was a company like startup company, Atina Markopoulos from University of California, Irvine is trying to do something like this, right? And it's we call it like in Texas A&M, it's Kyle Field. We have like a huge football field, and like it's 100,000 people, and of course like it overwhelms cellular networks, right? And it overwhelms like Wi-Fi, and people kind of think maybe we can do something peer-to-peer to improve performance, right? Everybody wants to see a replay of particular kind of piece of the game, right? And another kind of application for this problem, you can think about it as secret sharing, right? So suppose those packets, it's basically not a data packets, but just shared keys, right? So suppose we have like, we came here, and everybody has some keys, right? But we don't have like one key that's shared to everybody, right? But we have some keys, for example, I can share some keys with Marcella and some with Danila, right? So, and those keys, like for example, this user knows some shared randomness with this user, right? And this user shared this with this user, but not really one key that's known to everybody. And now we want to obtain this shared keys, right? So how this problem helps? Because by exchanging this information, everybody will know everything, but only limited information in some cases will be exposed to an adversary, right? So suppose we have, and I will talk about this later in this talk, but suppose we have some bad guy who listens to this, right, and can intercept all packets transmitted over the channel. So what happens in this case, right? So everybody will get 3 degrees of freedom, right? So because at the end of the exchange, and this is a solution for this case, right? Again, they have just 2 transmissions. You can again verify that by using those 2 transmissions, everybody will know everything at the end of the game. But if you have some bad guy listening to us, this guy will obtain those 2 packets, right? And everybody else will obtain 3 packets, right? So we see that we have, and we know what the bad guy gets, right? So we just kind of, this guy gets some subspace, so we take a normal to the subspace, this is your shared secret, right? So this is basically related to this secret shared problem, right? So it's kind of will be useful in this scenario as well. Okay, so it's kind of motivation, so we know it's kind of formally defined problem. So what we need to find out here is basically how to implement the scheme. So who is like determines the schedule, who is of course like schedule an event like just the number of transmission, because order of transmissions is not important, right? Obviously. Again, very simple observation that when you transmit, it's no point like every combination that you send, it will be just combination of packets that you have, right? It's no point to kind of combine packets that you overheard from the channel, because this is the public knowledge, so you just transmit the combination of bits that you have. So in this problem, basically, we need to kind of determine who is going to transmit. And another, we need to determine the code. But what I'm claiming is that determining the code is actually not very hard, right? So what is kind of main point of this problem is just to determine who's going to transmit. So anybody has an intuition why code is actually easy in this case? And it was non-trivial for index coding, right? So for index coding is basically all problem because we don't have really a scheduling problem, because we have only one kind of agent or kind of base stations that can transmit, right? So it's not kind of no point to determine how many need to design a schedule, and all complexity of that problem was in the code. So here the code is not really a problem, right? So why code is not a problem? Yes.
Maybe because
maybe you kind of got it. It's no scores here.
Okay. You can use MDS.
Yeah, so MDS is not clear because you don't have somebody who knows everything, right? So basically I will talk about, and I kind of talked about this in open kind of problem session, right? So yeah, in base station I kind of, if the same problem in base stations, I have somebody who knows everything, yes, this guy can use MDS and stuff like this, right? But you're actually kind of right, but it's not immediately true, right? Because I don't have somebody who knows everything. It's not like single scope. Right. Okay. So what other, like somebody who doesn't? Okay, guesses, right? We can say like crazy. So will random code work in this scenario? Guys, this is cool, right? Just guesses, right? So it's okay to guess. So what do you think? What is your intuition tell?
Yeah, you have basis and you need like a number of linearly independent equations and then you code it.
Right. Yeah, so random code will actually work well, right? So code design is not really a problem. And why it's not a problem? Because we can reduce it to multicast problem, right? So people like didn't like reductions, but in this case, it's actually a simpler version of multicast. It's nothing here, right? It's even simpler than multicast when you think about this, right? So you know, like multicast network coding, right? And it's no topology in the network. It's just very, very simple topology, which just includes a simple link. So basically, I can encode this topology as a multicast structure, right? And basically, in this example, shows this reduction between this problem, right, direct information chain, to kind of traditional network coding problem, traditional multicast problem, right? So how I can build this reduction is pretty trivial, right? So I have just one single source node. I have different packets, right? So X1, X2, and X3. And then for each node, I will have a set of senders. So this level will be 3 senders and 3 receivers, right? And then I will have bottleneck node W, right? So every sender will send V1, V2, and V3, right? And this will be kind of capacity of this link will correspond to the number of transmissions, right? So once I determine, just 1 second, right? So when I determine how many times each one transmit, I can determine the capacity of these links, right? So once I know the capacity of this link, this belongs to multicast problem. So again, this is a receiver. The receiver gets some information from this kind of correspond to wireless channel, right? So W basically this node will know all subspace that is transmitted over the channel. It's made available to all terminals. And all terminals, they also have side information. For example, T1 knows X1 and then X2 and X3. So it's basically will be this link of capacity 2, right? And basically those two problems are equivalent, right? So it's kind of, I don't want to waste too much time on this, but you can kind of later on come back. Yeah?
So in the network coding model, the coefficients of the first layer of edges and the second layer of edges should be 1, right?
Yeah, so basically, so here we kind of assume that this packet is uncoded. It's actually very good, yeah. So network coding is basically just on this part, right?
But it's not trivial then that random coding will be sufficient.
No, it's trivial that it's still sufficient, right? Because I can assume without loss of generality, right? So in general, right, you can use random code here, but it's not needed. You can say like, I can determine this code, right? You're actually right, it's a good point, right? So here I am kind of insisting on transmitting X1, here I am insisting on transmitting X2, right? And then I can use random coding for rest of the edges. Actually, only edges that actually need to do coding is those 3 edges, right? Because all other edges, they don't have something to work with, right? So coding. But it's still like it still satisfies this mean cut condition and right? And it's also like by using this reduction, we will see that the field size will only depend, so I don't need like an well-known in multicast network coding that the size of the field depends on the number of terminals. So exactly the same, like kind of once I determine the number of transmission, I can basically solve it with a small field size which is no larger than the number of bytes. And actually to find this number of transmission, I can use large fields, right? Because then I can reduce this field by using this reduction. Is it clear? Okay, so reduction sometimes might be useful, right? So not only theoretical exercise. And we can also obtain some trivial bounds, right? So kind of people like bounds, right? Especially in this community. But unfortunately here we don't have like just one instance. We have multiple instances, right? So again, it's kind of a family of problems. It's not just one problem because for each side information you have different types of problems. But one of the straightforward bounds is definitely like a number of required packets, right? So if we say that each client is basically ni a number of clients known to a packet, number of packets known to a client, and then n minimum is a client, kind of poorest clients that have like fewer number of packets, like less degrees of freedom. So n minus n min is definitely low bound to all, right? Because just to satisfy this guy, we need to transmit n minus n1 and min, right? So it's kind of trivial bound, but it still will be useful to designing an algorithm. And also we say like if all clients have the same number of packets and min, right? So suppose everybody has two packets and total number of packets is 4, then we say like we need at least 3 transmissions. So we need to add 1 to it. And why is the case? why we need to add to here? Need to have this clicker so we can send text, you know. Okay, so suppose, yeah, I just kind of want to make sure that we're on the same page, right? So suppose here, like, yeah, here we have one is have one packet and it requires two, but suppose this guy would have like another, like suppose I just remove this guy, right? So consider the instance, right, in which we have only 3 of those clients, and this is not present, right? So in this case, what I'm claiming, n min is equal to 2, right? So everybody knows exactly 2 packets, and total number of packets is 3, right? So why we need 2 transmission? Why we cannot do just 1? What is the intuition behind it?
Because they don't have the same packets, so of course someone will need different combination of the other. Like in this example, if you only transmit x1 plus x3, so the x1 and the client having x1 and x2 can decode x3, but the other client can decode nothing.
Okay.
Oh yeah, it can decode.
So any other it's kind of, yeah.
So you trigger when the number of packets that you need to transmit is smaller than the number of nodes, right? Because then one node will not be able to, in this case,
Yeah.
if just one transmits, this one will not.
Sure. Yeah. Professor's help me so it's kind of like, yeah, it's a trivial, right? So it's not, yeah, it's basically when you transmit, right, you're not getting any information, right? So for example, this guy transmitting, right, it's not learning anything, right? So if I'm kind of saying something, I presume there are already users, right? So then this guy still needs to get this packet, right? So it still needs to be +1, right? Okay, and you guys information series, you can probably establish better bounds of those, right? So if you think about this. But it's index dependence, right? So we have some kind of formulas, right? But it's actually kind of, if you want to work on this, it's kind of, problem is that those bounds will depend on particular settings, but if you somehow can capture the properties of the settings and through those bounds, it might be interesting. Okay, and
there is no
universal bound.
universal bound. Consider all the bounds, you should consider the whole family of the NIs.
Yeah.
Otherwise, you cannot consider.
But you can still do like here, like, for example, you can have some property like n min and kind of express as an n min. Maybe you can partition it in like multiple sets and say, yeah, it's still possible actually, yeah. It's still possible to do it, yeah. But it will be complicated, it will not be simple. Okay, so, and then we present an algorithm, so what do you think, like, to solve this problem, is it a hard problem or easy problem? I just said a lot, maybe like no task. So how many people think it's hard? But you need to say hard or not. You don't say no. So how many people think that this problem is very hard? So can you take note people who are not participating and maybe not really So how many people think this problem is hard? Okay, and how many people think this problem is easy? So I have some people here. But the intuition is good, right? This problem is easy actually. You shouldn't be afraid to speak out. Right. So yeah, this is polynomial time problem, right? So it's and this is the reason because it's kind of similar to multicast, and multicast time problems are easy. Okay. So if you think about it, I'm kind of not going to waste more time on this, but if you kind of, as I said, like key point is determine who is transmitting kind of in this game, right? It's not really important what it transmits. Right? But we can figure out later on, right? If we got this schedule right, and schedule I'm saying just in terms of number of transmission because, as I said, like order of transmission is not important. Okay, and so basically, if you think about this in a way like little bit, right? I'm kind of pretty sure if I gave you like 2 minutes to think about this, you would propose some algorithm which looks like a greedy algorithm, right? So basically saying the richest guy needs to kind of share its wealth with others, right? So we're saying like the clients that have the largest degree of freedom, right, it's probably need to transmit to other people. Why? For 2 reasons, right? Because this client knows a lot, right? So of course, like if we have one client that knows everything, only this guy can transmit, right? So the problem is becomes very easy using MPS or your favorite code, right? And it will be done with that, right? But the problem is nobody really knows everything, right? And then clients that have largest, so in this example, this client has the largest degree of freedom. So this guy has largest knowledge, right, on the one hand, right, so it can help a lot of other people, but also it doesn't need too much, right, so other people kind of, because we want to be like, everybody needs to be rich in there, right, everybody needs to know everything, right, so it's not really important to have one guy rich and another guy poor, right, so we need kind of, in this case, it's kind of very socialistic problem, right, so everybody needs to accumulate this, right, to remove this. But it's kind of like very kind of a lot of equality here, right? Okay, so let's kind of work with this. It's kind of greedy algorithm in which we just pick a client that has the largest degree of freedom and make this client to transmit. For example, here, this client, for example, transmit x1 plus x3, and everybody will gain from this, right? And then this guy might not be rich anymore, or not richest anymore, right? Because after this, its degrees of freedom remains to be 3. And this guy gains 1, so now we have 3, 3, and 3, and 2. So now we can choose, for example, among those two, and eventually everybody will know everything, right? So, and kind of, you can actually, it's a linear, kind of, in this case, we present kind of linear algebra formulation. You can also do it in information theory, right? You can basically capture the uncertainty in this client by entropy, and then say just each client with highest entropy will transmit and stuff like this, right? I'm pretty sure you can write it down pretty quickly, yeah.
How can we know that each node has like how many number of packets?
Yeah, so we assume here, right, so it's probably our people, practical people will kind of object to it, but he assumes that everybody knows what everybody knows. And it's kind of, I'm claiming this can be done if those packets are large, right? If those big movies, right, so it's like downloading illegally some Netflix, right? And so basically it takes like only few rounds to exchange it.
Kind of handshaking before that?
Sorry?
There should be a kind of handshaking before that?
No, it's maybe some kind of exchange before that, which is saying, oh, who knows what, right? Or kind of you can think about being the bus, right? So we kind of receiving some packets, and then our bus went out of coverage, or plane or train, and then we say, oh, who has what? Let's try to reconstruct it. Let's try to do it quickly. Let's try to synchronize, but first like, okay? Yeah, it's kind of another interesting problem what to do. Actually, in this problem, unlike index coding problem, knowing exactly who knows what, it might not be like really essential, right? Because you can use random coding. So basically, more information is, yeah, to some degree, right? It's important, right? It's not completely unimportant, but it's also important how many degrees of freedom you have. But as we said here, if, for example, we know, yeah, so this greedy algorithm might not necessarily work, but some variation of this greedy algorithms work. So if you know who is the richest guy, this guy can transmit at least in the beginning, right? So, and then that's not really important what other client. Okay, it's less important, let's say, very kind of hand waving, but less important than in index coding. Okay, and basically work with Chung Chang on a variant of this problem. So he basically kind of have completely information theoretic formulation with all these permutations and entropies, and basically it's also captures some dependence between different random variables, right? So it's not only like this particular instance of the problem, right? But you can think about that those people, like for example, this client and this client, they share some, they have some correlation, right? So they have some kind of random variables, but those variables are correlated, right? So you can basically describe this in this sense, but we kind of abstracting it out. Okay, and they call it omniscience problem. So omniscience problems that you kind of want to achieve that everybody know everything. Okay, and so why greedy algorithm won't work, right? So in simple sense, you can kind of think about in this instance, and in this case, this is the richest client, right? So suppose this guy knows 4 packets, those clients know only 3, and this client knows 2 packets. So if we let this guy to transmit, suppose it's transmitting x3 plus x4, right? And basically we can kind of try to do greedy algorithm in which client with largest degrees of freedom transmits, and we also ensure that this packet is constructed in such a way that all other clients then learn something from this transmission, right? So it's kind of reasonable to assume that if I'm transmitting and I have larger degree of freedom than Danilo, right, I always can tell him something, right? And if I have largest degree of freedom than somebody else, right, so if my subspace, actually it's true, if my subspace is different from anybody else's subspace, right, I can kind of give something new to this guy, right, so, or person, right? So, and by basic principle of network coding, if I can give somebody to each person individually, through coding, I can kind of make it to everybody, right? So I can basically transmit a coding combination that everybody will learn something, right? So we can always design this algorithm that the richest person will transmit, and everybody else will learn something about it. But it turns out even this is not sufficient for this algorithm. So for this example, if this guy, this client with 4 clients will transmit, for example, x4 for x3 plus x4, and this is client, everybody will, for example, this client will receive x4, this client will receive x3, this client will receive, it will not be able to decode something, but its degrees of freedom increases, right? It will have some subspace of size 3. So everybody making progress, right? But it turns to be that it's suboptimal, right? So for example, after this transmission, this is a wrong transmission, right? And you can basically, again, like it takes time to work out this example. We have only limited time. But it turns out that this packet is useless because if you're looking on those 2 clients, right, they know x3 and x4. And we know that those 2 clients, they have packets x1 and x2, which those 2 clients don't have, right? So if you kind of partition this network, like take those 2 clients aside, right, just partition kind of as Michelle talked yesterday about cut sets, right? If you have this cut set that divides those 2 clients from those 2 clients, you see that clients x1 and x2 must cross this cut, right? Because they know x1 and x2, those clients don't. So those 2 clients must make 2 kind of transmissions separately, right? So in this case, for example, for this solution, one of them, for example, transmits x1, and one of them is transmitting x2, right? But what we also see here is that they also need to exchange x2 and x3 between themselves, right? And it kind of turns out that basically is that instead of sending x3 plus x4, we can just have a fewer. So this is another solution with just 4 transmissions. We can just add this x3 to here and x4 to here, and it will basically kind of eliminate this transmission from x1 plus x2, right? x3 plus x4. So it's kind of like maybe it's a little bit brief, but I just don't have time to kind of, you can look on slides again and think about this. But it's kind of like an example why this greedy algorithm in its simplest form might not necessarily work. Right? Any questions here? So if this greedy algorithm in its simplest form doesn't work, right? So what algorithm will work? Okay, random code will work, right? So basically, the idea is to take this greedy algorithm. So the idea is that greedy algorithms that tries to, and if you think about it, right, I'm trying to take greedy steps, right? I'm trying to make sure that largest number of clients will learn something from my transmission, right? Yeah, so largest number of clients know something from this transmission. I kind of need to be careful that not to transmit something that will be kind of send some data that will be known anyway later on, right? So for example, x3 plus x4 is useless because it can be done for free later on, right? So it's kind of not really aiding to optimal solution. And it turns out that it can be done by random coding. Why random coding? Because in this problem, like in the multicast problem, the more I mix, the better, right? And it's completely different from index coding, right? And index coding, we need to be careful with mixing, right? Why it's kind of interesting combinatorial problem, because if we mix too much, we're creating too much interference that's hard to get rid of, right? So in this case, we kind of want to achieve this omniscience that everybody will know everything, right? And it's okay to mix as kind of as much as you want, right? Because the more you mix, the better, right? So the more information you do, and eventually everybody needs to decode everything anyway. So it's kind of maximizes the probabilities that metrics will have a metrics to be improved. Okay? So it turns out this random algorithm will work. So basically the algorithm is pick a richest guy, right, with largest degree of freedom, richest client, have this guy transmit like the largest kind of combination of a large field. And again, field size we don't need to worry because we can reduce it later on. So just pick like infinite field size if you want, right? So kind of transmit random linear combination over this field size, and then kind of evaluate of the second round how many clients have different degrees of freedom, and then just pick the largest client again and do this and kind of until then. So this algorithm will work with high probability, right? When we do random linear coding. Okay, so basically we can make some claims that this algorithm will work with probability 1 over n squared over q. And again, we can make it arbitrarily close to 1 because we can take this q that is pretty much very large, right? So again, like it's kind of trade-off between if you make it large. You cannot make it really infinite if you want to worry about the kind of computational complexity, right? Because it's hard to represent large numbers, but we can take it large enough so this probability will be small, but this again will not be zero. Okay, however, it's possible to using the same intuition to construct a deterministic algorithm as well, right? So in this case, random algorithm is not unique choice. It's will be just more complicated. So let's kind of prove, not exactly prove, but show why these algorithms work with high probability. And the idea is that we kind of saying that in each step, you kind of getting closer to the optimum, right? So with high probability. So for example, once you make this transmission, so you have one instance, right? So for example, here we started with this instance, and it will be some opt-I for this instance, and then we made this decision for this client to transmit x1 plus x3, and then after with this transmission, we arrive to another instance, right? Because some of the clients will be able to decode some new packets. For example, client number 3 will be able to decode x3, this client will be able to decode x2, so it's kind of like a different instance. But if I'm evaluating optimal for this instance, and I can make a claim that optimal for this instance, for this new instance, is less by value of 1 from here, right? I'm kind of on the right track, right? So basically I kind of reduce my optimal. And if I'm claiming this for every step, so eventually I will come to the case that everybody will know everything. Only problem we need to be a little bit careful that here we assume that all clients that have just packets, right? So here all clients can have packets and also linear combination of packets, and not necessarily in a systematic form, but it turns out to be not a big problem. Okay, and the idea is, again, I kind of will just describe it quickly. I'm not sure like what is the best picture for this. I'll just probably draw myself. So it's will be here, right? So why we can claim this with high probability? Because I'm even selecting a client that have a larger number of transmissions, I can compare things. I compare performance of this client. I'm kind of competing against optimum that I don't even know, right? So and it's kind of like used a lot and kind of give you some taste of proofs and algorithms, right? So you basically have some optimal solution. And in this case, this optimal solution, we have a certain number of transmissions, right? Okay? And then if I choose the largest client, right? So this client already has those degrees of freedom. So this is basically subspace known to this client, right? So this is row of this matrix. I can represent it by matrix. And row space in this matrix is basically the basis of what I know, right? In this example, I know x2 and x3, right? In this case. Just x2 and x3, but in general it can be more vectors. This is what I know. And this is the optimal solution, right? It's basically a solution that solves this problem optimally, but again, I don't know this, right? But what I know is that if I'm combining them together, right, I will be able to decode everything, right? So basically, it's not necessarily a square matrix, but it's enough degrees of freedom. If I know those vectors and I know those vectors, I can decode all of the vectors, right? Obviously, because it's an optimal solution, right? So now this optimal solution is not transmitted by one client, it's transmitted by multiple clients, right? Okay, so for example, this is transmitted by C1, this is transmitted by C2, and this is transmitted by C3. So if this client that I picked, right, and I picked this client with the largest number of degrees of freedom, if it makes transmission in the optimal solution, I'm lucky, right? Why? Because I guessed correctly, right? So I guessed correctly that this client part of the optimal. I don't know exactly which vector it will transmit in optimal because I don't know it, but I know that I can substitute it with a random vector, right? So if basically, so why the solution is optimal, we need to make sure that basically what I'm doing, I'm substituting some vector in optimal solution by some linear combination of those packets because this is vector that I transmit. All right, and the idea is if I can find some vector in optimal solution, right? So this is vector v and this is v prime and v hat. If I kind of substitute some vector in optimal by this vector, right? And everybody will be happy with this, right? Then that's okay, right? So this is step because this will be with the rest of the packets, everybody will be happy, and the optimal will be basically remaining packets in the optimal, right? And so in the new instance, I can solve it by opt minus 1 transmissions, right? Is it clear or I lost it? Okay. Okay, so this is a case that I need to repeat it. I don't know, just repeat it. Okay, so thanks for that. Okay, so basically what I'm saying is that suppose I have this instance, right? And every client in this instance initially knows some subspace, right? So we have a vector space, right, of 3 buckets, right? So it's dimension 3 in this case, very easy, right? And everybody knows something about this. This is knows like any subspace spanned by x1 and x2, right? It can compute x1 plus 2x2 and stuff, right? So, and I'm now picking the largest client, and this client I can just pick anyone because everybody knows exactly the same, right? So now I'm saying, okay, this is a client that I picked, right? So for example, in this case, it's knows x2 and x3, right? So let's just kind of focus on this one, right? So this is the subspace of this client. Now what I'm saying in my solution, actually let's kind of be consistent with this picture and pick this, yeah, x2 is yeah, this is one I picked. And basically what I'm saying in my solution, I'm transmitting this vector, right? So in this case, this vector would be x2 plus x3. So just simple case, right? So what I'm saying is that by doing this, I'm not kind of deviated from the path to the optimum. So what is the path to the optimum? The path to the optimum, I know, for example, in here it will be 2 transmissions, right? So this is the span of the optimal solution, but I'm not necessarily knowing the solution, right? So suppose I'm guessing its size, right? But I don't know what's going to be. But I know there is some optimal solution. So what is the optimal solution? This is a set of vectors transmitted over the channels that satisfy everybody, right? So this solution, like solution for every problem exists, right? So always possible to solve every solution, every instance, right? So and this is basically an optimal solution, right? It's kind of clear until now, right? So yes. Yeah, you can bound the optimal solution, but it will be different from each instance. It's not like a formula. You can do upper bound, as I said, like n minus n min plus 1. Lower bound, you can also say, right, something like what is yeah, it's a lower bound. It's lower bound, right? You can also derive upper bound. But it's hard to determine like exactly formula for the optimal. Right? Okay, so it's clear until now, right? So this is optimal, right? This I don't know, but I'm trying to guess it, right? So now suppose that somebody gives me, it's kind of a black box, I don't know what it is, but I can analyze it, right? I can say, okay, suppose it's kind of, just for the purpose of analysis, because of course algorithm doesn't use this information, right? So now I'm saying, okay, this is optimal, right? So some client's transmitting, right? So suppose somebody gives me the optimal solution, that's client 1 and 2, right? So in this case, I kind of guessed it correctly, right? So basically, I'm kind of putting this solution, right? And this optimal solution, client 1 transmit and client 2 transmit, right? And I'm kind of choose client 1 transmit, right? And I'm kind of lucky, right? It's just one case. I also need to consider a case when I am unlucky, right? All right, so if I'm lucky, right? So basically, I can kind of say, okay, this is vector that I transmit, and this is vector and optimal, right? And it's kind of can be a different vector. Maybe an optimal at x1, x2 plus some 3x3, right? I don't know, right? So it might be a different vector. But what I'm saying is that I can substitute this vector. I can obtain a new optimal solution, right? It's a new solution. It will be different from this optimal, but it's going to include this vector and the rest of the optimal solution, right? I can do this. And what I'm claiming is that after I do this solution will also be good with high probability, right? And why? Because this is a random vector, right? And then if everybody is okay with this solution, right? So everybody can, so suppose I exclude this vector from optimal solution, right? Then everybody else, right, will missing 1 degree of freedom, right? So, and then I'm saying, okay, this is a random vector, this high probability is will basically kind of happen, right? So this is basically kind of an intuition. It's not a complete proof. There are some few details, but it's not very complicated, right? So now what we need to do is basically consider the case in which one is not transmitting here, right? Right, it's not necessarily true. For example, those optimal solutions, it's like many solutions in this case, it's not necessarily unique. So somebody gives me like 2 and 3, right? So if 2 and 3 is basically what I'm kind of can say here, I'm looking on this bucket, right? And this is where I'm using the fact that this client has the largest degrees of freedom. This client will use some vectors from the optimal solution, but will not use all vectors from optimal solution. And this kind of comes out from this lower bound, right? On the size of the optimal. Right? Because this is the largest client, right? So for example, here, you see that the optimal solution is the size of please 2, but this client only needs 1 degree of freedom. So in general, largest client, so for example, it's n max, and it will need n minus n max degree of freedom, right? And we can say that it's always strictly less than optimal. Why it will be strictly less than optimal? Because if you have a client that have strictly less degrees of freedom, this client will require more degrees of freedom. So then it's kind of, to satisfy this client, I need to have largest, right? So for example, I have 10, n is equal to 10, and this is equal, like n max is equal to 3, right? So this client will need 7 degrees of freedom. If I have client that needs 2, this client will need 8 degrees of freedom, right? So if it's 8 degrees of freedom, it's larger than 7. So opt is at least 8, right? And it's larger than this, right? If everybody has, like in this case, everybody has the same degrees of freedom, then, as we said, like it's +1, and this makes sure, okay? So now what we're saying is that this client will consume, so from the optimal solution, it will not need all vectors, right? So this client, we know that I'm taking this client, and I'm concatenating this with optimal, right? I will be able to decode all clients, all packets. But we see that there is some dependency because I have 2 degrees of freedom, I take 2 from here, but I need 4, I need only 3, right? So some of the vectors will be, so basically only one of vectors here will be useful. So one of the vectors, right, will not be useful to this client, right? So this vector will not be useful. So if this vector will not be useful, what I can say, I can rearrange my schedule in such a way that first this client, right, so I'm kind of saying, let me transmit all those clients, right, all those packets, and this client will achieve kind of omniscience, it will know everything. Once it knows everything, it can satisfy all other clients. So basically, by transmission of this, I can satisfy everything. Okay, this is kind of like intuition. Okay, and this is kind of how this problem can be solvable. And again, like if we solve every step, right, so then we can, with some high probability, like if we make it Q large enough, solve all the steps. Okay, so this is for this problem. Now let's consider a special case in which we have an eavesdropper, right? And as I said, like it's related to this key sharing problem, and it's kind of famous work on key sharing. It's related to this. I think it's Narayan. What is it? Cesare Narayan. Right. So it's kind of related to this problem of a secret key exchange, but this is kind of more like from linear space, linear algebra perspective, and their work is more from information theory, right? But and that's kind of slightly different problems in nature. Okay, so now suppose, kind of in this case, we can assume, reasonably assume that somebody will try to listen to this. And I said, like, everybody listens to this will be able to obtain those linear combinations transmitted from the channel. And again, like, we will know more information than this person, right? So we'll have some keys. And actually, it was really interesting work by Tom Carcade, in which we said, like, we don't need many keys. Instead, in this case, number of keys we get is exactly n minus opt, right? So everybody will get, like, a lot of shared keys. And actually, it's not true that always you can do it, right? So it's opt is equal to n, we will not get anything, right? So, but in this case, it's not possible to get, right? So we need to have some shared keys to get we can get like pairwise shared keys, but if we don't have any keys in random, right, it's not necessarily always you'll be able to share some keys, but in this example we can. But also like it's prescribed number of shared keys, it will be n minus opt, right? So if we have like n and 10, and we have opt is 5, so everybody gets 5 keys, 5 shared keys. The question is, suppose you only want 1, so it's Tom Carcade work on this and show that it's half. But it's not half to do 5, right? Okay, this is the idea, right? And now what we can do, right? So we basically can consider, okay, and in my formulation I'm talking about this fixed secrecy. So we consider that those are not packets, keys, or we can basically assume that those packets are randomly distributed, right? So if they're randomly distributed, I can basically use them as a keys, right? And instead of strong secrecy requirements, so strong secrecy then requires that an eavesdropper will not get any information about those keys, right? And of course, I cannot achieve here, if those are just packets and not keys, right? I cannot achieve strong secrecy because on all packets, because adversary will see the combination of those packets, right? So I cannot achieve this in this case. In this case, I need like special keys shared between different clients. What I can achieve is weak secrecy requirement. In this case, for example, I'm just protecting a single packet, right? And if adversary is just interested in decoding individual packets, but not combinations of those packets, I can achieve this in some instances. Yes?
It's for all eyes.
Yeah, it's for all eyes, definitely. Yeah. So in a more general case, you can consider some cases with specific i's, but it makes it less interesting, right? Yeah, it's true for all i's, right? So I want to protect all individual packets, and in some generalization of this, I want to protect like small set of packets. So basically the idea here is that, so adversary will get some linear space, right? So some linear subspace of those packets, and I'm looking what is the vector in this subspace with the smallest common weight, right? So for example, in here it's 2, right? And 2, in this case, I can only achieve this for every packet. So adversary, if we're looking on those 3 packets, it cannot decode any individual packets, but it can see combination of 2 packets. So I can have a better solution for the same problem, okay? It's the same instance, but here, okay, in this space, the minimum weight of any vector of this space is 3, right? And if it's the minimum weight of any vector is 3, I can protect any subset of packets of size 2. So, and this is better than just protecting 1, right? So the idea is like in some settings, right? Suppose we're exchanging those files, right? It's okay to expose like a combination of those files, but it's not okay like to people be able to do. So suppose we're sharing some movies, right? So if somebody getting like X sort of 2 movies, it's probably not something very useful, right? It's not information theoretically secure, but in practice, right? I kind of try to watch this movie, it's probably not going to be much information, right? If those movies are random movies, right? Okay, and the idea is to basically maximize this, right? So we want to maximize the minimum size, this maximum problem, maximize the minimum weight of the vector in this subspace, right? So this is the problem we're trying to do, okay? Is that clear? Okay, and as I said, like we kind of want to generalize this, and we have a parameter g, so we want kind of client to kind of adversary to have no information of any client, every subset of packets of any of limited size, right? So we consider all subset of packets of size g or less, and kind of adversary shouldn't get information about it. Okay, this is the problem that we're trying to say. So this solution is too weakly secure because any subset of packets of size 2 will not be known to the adversary. Okay, and you also can kind of think about this problem in the sense that adversary might have some information about some of the packets, right? So for example, in this case, if adversary has side information about x1, it can decode x2, right? But with this solution, if adversary has some side information about x1, it still cannot decode any other fact. Okay, so this is basically the motivation. And it's kind of related to this matrix completion problem that I talked in open problem session, so it's kind of reconnecting to kind of setting that I was interested in. So it's basically kind of problem is that it kind of can be seen, right, intuitively. If you're looking on this, right, so suppose I'm just worrying about secrecy. I don't want to minimize the number of transmission. I'm not worrying about like energy life and stuff like this. I just want to exchange those packets such that adversary will know as least as possible about what I'm transmitting, right? But it's kind of can be seen that basically the goal, even if I'm not explicitly asked to minimize the number of transmission, right, it's still better to minimize the number of transmission. So somebody can give an intuition why it's true. Yes?
Give the adversary
less kind of, yeah. So it's kind of like intuitively it's clear, right? So less transmission we make, the less information the adversary will learn about what we're trying to do, right? So it's basically kind of the same problem, right? So it's the same problem with minimizing the number of transmission because it's kind of turns out that to solve this problem, I can just take a solution for information exchange program, right? And just try to kind of, as I said, in this problem, what is important is schedule. And I just kind of, any schedule that ensures optimal solution in terms of minimizing the number of transmission, I can make the solution works for the secure problem, right? So basically, secure problem is just a matrix completion problem because, for example, here, I just determined, right, I'm just putting this adversary aside and solving information exchange problem and say, okay, for information exchange, this one I need to transmit 1 time, this is 1 time, and this is 1 time. And then I'm just throw away this code that was produced, just kind of using information about number of transmissions and put this in a matrix, right? And this matrix of size opt and length n. And in this matrix, we have each row will correspond to a particular client. And so for example, here there will be client 1, client 2, and client 3, and we'll have forced zeros on these rows, right? And forced zeros is basically because this client only knows x1, x2, and doesn't know x3 and x4, and knows x5 and x6, right? So those will be don't cares in which I can put any value I want, because this will correspond, first row will correspond to transmission on the first client. The second row will correspond to transmission on the second and third, right? And now I want to maximize the minimum weight of the packets in this subspace, but it's actually an MTS problem, right? So like largest, so the mean max means that I can achieve is actually kind of n minus 1 plus 1, right? So in general case, I can be able to, and it actually can be shown that it's always possible to achieve this, right? So if your solution is O, it's always possible to achieve this minimum distance or minimum weight of the code. It will be always n minus 1 plus 1, right? So this is basically a problem. We just forget about this exchange, and we'll just walk into this matrix completion problem. So again, this matrix completion problem is kind of different from what people in coding theory usually do, right? Because they have complete freedom. Kind of like you need to design MPS code, right? You can do it in systematic, non-systematic way, but nobody forces you to have specific constraints on this generator matrix. Maybe in the constraint codes they do. But here we have very specific constraints on zeros, right? And this matrix actually completable to MPS. So it's possible, like again, it requires proof, but proof is not too complicated. If we obtain this matrix from the solution of independence exchange program, this matrix is completable to MPS. So this basically means that if I choose those vectors, right, appropriately, it's possible to obtain an MPS code, right? And as we said, like condition to this is this matrix cannot contain any rectangles of size larger, like the dimension of this rectangle is larger than n plus O plus 1 in this case, right? So we cannot have in this matrix, for example, all column zeros, right? Because if we have all column zeros, this matrix will not be completable to MDS, right? Or we have a rectangle by time 2 by 2, this also will not make it completable by MDS. But if we obtain this matrix from the solution of this information exchange problem, it's kind of easy to see that it will not contain those forbidden rectangles. Right? So again, the problem now is actually the problem is interesting by itself, even without connection to this information exchange. And again, given a matrix, just kind of find those access completable. Okay, so yeah.
Just a condition, but it seems to lose.
Sorry,
the A plus B greater than of plus 1 is just a condition.
No, it's necessary and sufficient conditions. Yeah, so it's necessary, right? Clearly, if you can contain rectangle by, like in this case, 2 by 2, I can find you a matrix that determinant just identically equal to 0. Right? And if it's kind of, if it doesn't contain those rectangles, I can show by using random coding that it's possible, right? And one of the solutions here to complete an MDS to have a random code, right? So I can pick those x's at random, and with high probability, I will complete the matrix to MDS. And it just follows again from this basic principle of network coding. If I take any opt by opt submatrix here, this matrix, this polynomial, I can consider those x's just as variables, completely independent variables. So if I pick those elements, kind of write the determinant of this matrix as a multivariate polynomial, it will not be identically equal to 0, so I can satisfy each matrix separately. If I can make every matrix happy separately, then I can make all of them happy, right? Okay, so the problem with random code is that, yeah, those are forbidden rectangles, right? So if we have those rectangles, there's no way we can complete it, but if this matrix is kind of obtained from this information exchange problem, we'll make sure that those rectangles will not appear here. Okay, so random code is fine, right? This will work. The problem with random code is hard to verify that what we get is good, right? And the idea is that finding, like determining if a particular code is an MPS code is a computationally hard problem, right? So we cannot do it efficiently in polynomial time. And also it requires high field size. And high field size is just follows from multiple constraints that we need to have. We need to satisfy exponential number of submatrices. So number of submatrices is equal to n choose opt, which is an exponential number. So the field size is exponential in this case, and also hard to verify. So what we want to, and it's kind of still open problem, right? We can do some calculation of field size that we need, right? And And the idea is to, can we find some construction, for example, zero error construction, or at least random constructions that I can efficiently verify. And we can do it like by using kind of nested fields. For example, if I field like some element from GF2, this is from GF4, but not in GF2, and stuff like this. It's easy to see that it's going to work, but field is double exponential. Yeah.
But can't you use Gaby-Dolin codes to make?
Yeah, we tried. It's kind of still not obvious because we need to this properties that Gaby-Dolin codes that every submatrix, even small submatrix has full rank, but it's not true for Gaby-Dolin codes.
Okay.
But
We can make it
it's
up.
kind of, yeah, we kind of talked about this with Danila, maybe we can figure out until end of the school. But and Gaby-Dolin codes also will have a pretty large field sizes.
No, the field size will be very large, but it's
Yeah.
not zero error.
Yeah, but that's one of the direction, but it was not immediately obvious to us that it might be possible to make it work out. But that's kind of like one obstacle was its large field size still, and then it doesn't have, we needed this property that every small submatrix will be full rank, and that's not true for Gaby-Dolin. So we kind of want properties that more like Cauchy properties that every submatrix is full rank, which is not true for one and one. If you know some subspace codes that have this,
We can
glad to hear it. Okay. Okay, and so basically the solutions that we wanted to do, why not take a code that we know MDS, right? So people have a construction, they don't need to work hard to modify this code. For example, if you take a generalized Reed-Solomon code, or Reed-Solomon code, right? And say like, okay, let's just kind of this code, let's just use this subspace spanned by this code. Right, so in this subspace, you always have a matrix. So suppose this is a matrix that we need to complete, and we call it configuration matrix, right? So suppose for this value of configuration matrix, right, there will always be code which are zero in those two coordinates and non-zero. It's only exactly one code word on this, up to some kind of constant factor, right? And this can be done by just performing row operations. So, and it's true for every row. So we take this code, we multiply it by this matrix, and we get what we need, right? And basically we done with that, and it's really be nice, right? Because this code is not the we can verify it mathematically, right? It's just a determinant to some very nice formula, and we know this will be full rank, and we kind of solving our problem. And the problem is that this matrix is not necessarily full rank. If we do this, right, this might be not a full rank matrix, even if everything else is look nice. This is a valid configuration matrix, and this is a valid code. Okay, and what we kind of, again, I kind of talked about this in open problem session, but we kind of trying to see, and it's kind of turns out to be a really, really interesting problem even from mathematical perspective. So suppose I'm leaving those, like I'm taking just generalized Reed-Solomon code and leaving those variables as variables, right? So basically I can choose them as I like, right? So suppose I'm not fixing, like in previous example, those elements are fixed, right? So we say like if I'm choosing them, right, even if they're different alphas, right, it doesn't, because this condition is not enough to make this matrix full rank, right? To make enough to solve, to complete this matrix. But what if I'm just leaving them open, right? In this case, it's just variable. And what I want to see, like in this case, like everything is determined by those alphas and determined by this configuration matrix. So as a function of this determinant has very nice structure, right? It can be written in kind of, I don't want to spend time because I talked about this in the problem solving session. Right, it's very really nice structure of this determinant, of this transformation matrix. And it turns out that what we want to prove is basically that this matrix is not a zero polynomial, right? It's just not identically equal to zero, right? So because each entry is a multivariate polynomial on those alphas, and determinant will be kind of huge multivariate polynomial on those alphas. And what we want to prove is that if this configuration matrix doesn't contain rectangles, this kind of determinant of this matrix is not identically equal to zero. And it's really annoying that it's kind of hard to problem, right? And it's kind of like if you think about this, right? Yeah.
Just a question. Do you know the rank of the matrix?
Rank which matrix? This one?
This
This matrix? Yeah, it's incomplete matrix, right? So how we can talk about rank?
this
So,
is how do you know? You don't know what is the rank of that matrix?
no, I wanted to be not only full rank, I want to be much stronger than this, right? I want it to be MDS, right? I want that every submatrix is full rank, right? This is my goal, right? So this is just a configuration matrix, just saying here where the zeros are, right? So my goal is to complete this matrix, but not only it will be full rank, it will be MDS. Yeah. Do you what? Yeah, okay, I know how to do it. Right. We spent like 1 hour doing this. Right? Yeah. This matrix, as I said, like this matrix, if you, as I said, like this problem is interesting by itself, but if you kind of relating to this exchange problem, this matrix is exactly a solution to this information exchange problem. I'm just speaking like each row will correspond to a particular client, and 0 will correspond to coordinates of the packets that are not known for this client. Because this client can transmit, yeah, this matrix, everything here is known. Yeah, so we know configuration metrics, and you can kind of pick a code of your liking. I just kind of what I want to really kind of make me happy if we can find something over a small field, some construction, right? Not something like random that hard to verify. If I can kind of really design that will work on a small field, and I don't need exponential number of steps to verify it. But everything has a problem. Okay. And it's so basically kind of just 2 minutes conjecture and mathematics. So this can be seen as a kind of coefficients of a polynomial that has roots in particular places, right? So for example, this is a polynomial, right? It will have a roots in place 5 and 6, right? This polynomial that described by this row will have roots here, 2 and 3, 3 and 4, sorry, and this polynomial 1 and 2. And then basically saying if we have a bunch of polynomials, and suppose they are independent, they're dependent, right? So suppose like we have 3 polynomials are dependent, but any 2 are independent, they must have a shared kind of common root, right? But it's kind of makes it really interesting problem. Okay, so I have 10 minutes. Just kind of, if you want to discuss this, you're welcome to talk to us, right? I kind of want to spend another 10 minutes unless you have any questions. Okay? So kind of another variation of this problem, right? And again, like this area is rich kind of an interesting problem, right? You can consider eavesdropper, but you can also consider that some of the clients are adversarial. Okay, so suppose we have a malicious guy that participating there that we don't want to share movies, but this person doesn't want us to kind of be called to those movies. Somebody like really concerned about like intellectual property rights and basically make it harder for us, right? And we don't know basically this person is maybe it's the right person, right? I'm not saying that necessarily better. So this person, it's not, of course, I'm not saying that this is a bad person, right? It's not identifying itself and trying to behave as a normal guy, and but it sends wrong information, right? So it basically decided that basically this guy sends this and this guy sends this. Actually, nobody asked how we decide, and in this case, it's kind of a centralized algorithm, right? So suppose we have one person can kind of gather the side information known, like just indices of packets known for everybody, and then say, okay, you transmit this and you transmit this, right? And of course, it's like possible to make a distributed algorithm, but just kind of first order of kind of dealing with this problem, just talk about centralized. And when this broker or somebody who decides who is going to transmit what, sending to this guy, okay, you're transmitting x2 by x3, but suppose it's kind of substituting from, instead of transmitting like real x2, it's just transmitting x2 hat, which is not real x2, right? And this may be like an honest guy, just kind of have its data corrupted, right? So suppose this disk is corrupted, right? Or kind of you can consider many scenarios. And the problem is like, can we design an algorithm that will basically be resilient against such kind of an adversary? And of course, we only limit kind of if everybody is adversarial or kind of has an coding theory more than some of the people are adversarial, no way you can do it. And can we design an algorithm that will be able to recover correct packets even if one person is adversarial? Right? Okay, and it's kind of like related to error correction, right, on the channel, but problem here is that if some person is transmitting 2 packets, it can make 2 errors. So it's kind of unequal, right? So we're basically saying it kind of depends on the schedule, right? So if, for example, adversarial client doesn't get to transmit anything, they actually don't need to do anything, right? So because we're lucky in this case, right? So we basically, it's adversarial, but this guy is not getting to transmit. But on the other hand, if you have one person transmitting everything, and this person in adversarial is really a disaster, right? So basically, it's kind of unequal number of errors in this case. Okay, so let me ask you, like, just we have a few minutes, but what is it called problem always solvable? I'm asking only trivial questions, right? So I'm just going to make sure that you understood the problem, right? So again, we have exchange, so we have set of clients. Each client have a subset of packets in some ground set, and we want to basically design a scheme for exchanging this information using a shared broadcast channel, and we want that in the end everybody will be able to decode the correct packets, and we have a limitation that one of the clients can be adversarial. So anyone can be adversarial, but not more than one. Okay, is it always possible?
Well, if you only want to test for x2, then it's
Right, right. So it's not always possible, right? So because if I'm only guys that have x2, right, nobody else has x2, right? So how we can decide if it's right? Right. So it's okay. And what is the condition needs to be? Yes. So I'm asking you a question. You're going to discuss.
Summary but how these things are used, like how these things that
Yeah, the coding needs to distinguish us, right? So how we correct data on a channel, right? Nobody tells us that there is an error with this, right? So we need to design a coding algorithm that design this kind of does it, right? Yeah, and this client doesn't say like doesn't put like a hat on his say I'm malicious guy.
So if we put the adversary aside, the rest should have a complete base of subspace.
Oh, it's actually a good idea, right? It's a little bit stronger than that, but I'm kind of looking for trivial answer, right? So what is a yeah, it's kind of actually in a good direction. I'm just way ahead of what I asked. But can you just formulate the trivial condition on 7? Yeah.
You must have at least 2 copies of each time.
Okay, so will 2 copy be enough? So suppose I have x2 and you have
Just
x2.
copies except malicious.
How many copies?
2 copies except malicious.
Okay, so how many is 3 copies, right? Okay, yeah. So 2 plus, yeah. So basically everybody can be malicious, right? So 2 copies are not enough, right, to correct. You can detect. It's kind of, basic stuff, kid stuff, right? So basically if you have 2 copies are not enough because we have copy, right? So we don't know who is malicious, right? So then we see you can see some inconsistency, right? I'm saying x2 is equal to 3 and you're saying x2 is equal to 5, but we cannot decide who's wrong and who is right, right? So, okay. So if you have 3 copies, right? So then what we can do, right? If you're not worried about number of transmission, we can just do, right? Vote, right? So we do a majority vote. Right, so voting is not always good, but in this case, right, so we can do a trivial algorithm. A trivial algorithm is basically just to have 3 copies of the client transmitted by 3 different people and just take a majority vote, right? So just based on the largest number, and then we know who is the bad guy. Right? So should be. Right, okay, and but of course, like this is a very kind of not a kind of really optimal algorithm. Right? So it's a lot of redundancy here, and we basically can do much better, right? So, okay, and the question is like, first of all, what we can do, right? So this is a trivial solution. If you do a majority vote, so we can see inconsistent packet, right? And the idea is that we can do it better. So, for example, in this case, we can do it with fewer transmission because if we're sending 3 copies of each packet here, so we have 3 packets, so we need to make 9 transmissions, right? So and here we just can do it with 2 transmissions. Right? So you can also verify that here, this solution can be resilient to any one adversary. Okay, and this exclusion rule is actually very nice, right? So you just need to exclude more packets than me. And one of the observations, if you're just talking about the ratios, right? So suppose we don't have errors, but one of the clients can be like unreliable, right? So I tell Marcelo to transmit, and I don't know really like he's Brazilian. I'm just and so kind of he might transmit, might not transmit. Okay, and so in this case, I want to be kind of robust against this, right? And saying, okay, I will design a solution such that I can reconstruct the optimal, like all those 3 packets, even if one of the clients is excluded, right? So this will kind of correct erasures, but this will not correct errors, right? Because we'll not be able to reconcile. So it turns out that to correct errors, we can use this exclude 2 property, right? So basically, if we can design an exploration exchange algorithm that even if 2, and it's kind of like similar to coding theory, right? So you have like twice redundancy as much as number of errors. And just in this case, it's a little bit more complicated because it's, we don't have somebody who knows everything, right? And you kind of need to be, it's kind of need to take this into account. The client can make a larger number. And it turns out that this problem becomes hard, right? So it was polynomial time solvable before, but once you introduce this and you insist on this condition, it's hard. And I have some reduction from vertex cover program if you're interested, it will be in the slides. And also to verify this condition is not extremely hard, right? It's kind of, if you think about this, it's also will be in the slides and you can think why it's true. And I just kind of wanted to conclude before this buzzer going on, right? And basically this kind of field, as you see, like it's a lot of connections to different problems. And I appreciate you coming and your interest and kind of waking up very early for some people and coming here. But you can see that it's many possible extensions and many open problems and many stuff to work on. So if you're interested, you can discuss more, or you can just yourself formulate your own favorite problems, and maybe in the next school we can kind of have nice results. Okay, thank you very much.